we've basically introduced the fundamental ideas and fundamental concepts of this world of electricity. And you remember there are two sets of fundamental quantities, right? Some vector quantities and scalar quantities. So I will start from that. So vector quantities, you remember we introduced the electric force, then also electric field as the force divided by the value of the probe charge. And then at some point we decided to switch to the scalar quantities. Instead of force, we introduced the potential energy, electric potential energy. Both of these quantities describe interactions. So pretty much we're replacing quantity with a similar quantity. We're not replacing apples with oranges, right? Then, instead of electric field, which describes electrical aura, we introduce the vector quantity, the electric potential. Again, they describe the same thing, but vector quantity and scalar quantity. Then, of course, fundamental formula how we can find electric force. If you have a charge exposed to some electric field, Q times E gives you force acting on the particle which is exposed to the electric field. Similar, if you have a particle exposed to, again, electrical aura and you know the value of the electric potential, charge times the value of the electric potential gives you potential energy. Right? Okay, then, so for particular systems, point charge and parallel plate capacitor, so all these things. So force for, of course, Coulomb's law, interactions between 2 point charges. Of course, we all know that, KQ, Q over R squared. Then if you replace electric force with the potential energy, we derive it, and we got this formula. Potential energy of these interactions, KQ small times Q capital divided by R, first power of R. Again, vector quantity, scalar quantity. And then if you introduce electric potential, you just basically need to remove the value of the probe charge. You will get the electric potential at this point created by that point charge Q capital. It's a KQ capital divided by R. So very important things. Of course, we're going to use it. Then, if you have now a system of a capacitor, which give us a uniform electric field, right? So, of course, if you want to find the force, let's say you position point charge in the inside of the capacitor, of course, force can be found Q times E. It's essentially the same. Then, if you make a transition to the potential energy, Q times the value, this is the value of the electric field, times X. X is a distance to the point charge from the negative electrode. You remember that in your quiz, recent quiz, you had to use that idea, right? And, of course, this part, E times X, it's essentially the electric potentials, right? So if you take potential energy divided by the Q, potential energy divided by the Q, Q disappears, and you have the expression for the electric potential, right? So we used it just recently. Okay, so then, since electric field and the electric potential describes exactly the same thing, so of course we should be able to move back and forth between these two quantities. So if you want to move from the electric field to the electric potential, you have to integrate. Integrate between some arbitrary final and initial point. So when you calculate this integral, don't forget about this minus. You will get the potential difference between the final and the initial point. Right? So you can either, if you write down this as a function, you can integrate, or if you can plot electric field versus position, you can just calculate the area under the plot in order to get the negative value of the potential difference. Right? So again, don't forget about the minus. Calculate area, add minus, and that will be delta V between this point and that point, potential difference. Okay, if you want to move in the opposite direction, it's very simple. In order to get, for example, x component of the electric field, you just need to take a negative derivative of the function V with respect to x. Actually, it's a partial derivative. You need to differentiate only with respect to that particular coordinate, right? Keeping the rest constant. And the same y component. Okay, so that's some fundamental ideas. And then also, we introduce an alternative way of finding electric field, Gauss's law, right? So you can use this to find the electric field, or you can use Gauss's law. So if you have some charges, you can pick any, literally any, closed surface, but it must be closed. So essentially, it's a closed surface, not some closed loop. And so if you calculate this integral, which is essentially flux, electric flux, through your chosen Gaussian surface. So that flux must be equal to the total amount of charge enclosed by that Gaussian surface divided by our universal constant epsilon naught. And Q enclosed, in this case, it's a charge 1, 2, and 3. Charge number 4 is outside. We're not counting any charges outside. Okay, so that is also definition of the electric flux. In the simplest possible case, E dot A, this is in general, this is special case. Okay, and the last piece which we need for this exam, properties of conductors in the electrostatic equilibrium. So we spent like 2 classes discussing that. So if you have a piece of metal, first of all, they have tons of free electrons. They're free to move anywhere they want, or you want. And we found, so if you exposed to this piece of metal, if you dump some amount of charge or expose it to some external electric fields or something like this, right? So then electrons will move and distribute themselves in such a way to make electric field inside 0. Otherwise, electrons will never stop running. They will keep running and running and running to make net electric field inside 0. So then, if there are any excess charge on the conductor, that excess charge must reside on the external surface of this conductor. Right. Of course, distribution can be complicated, but that's another story. And then, since we also introduced the electric potential, we also just recently we proved that in the state of electrostatic equilibrium, electric potential inside of the conductor must be constant. Electric field 0, electric potential constant. Right? Okay, so that's basically the scope of first exam. So the first one is a little bit tedious. You remember the first 2 recitation classes we spent basically reviewing vector algebra. Let's do it one more time. Since it was like months ago. So this will be the problem number 1. Right. And so 2 charges. One is positive. Let me start with a picture. A positive charge, and somewhere over here there will be negative charge. Right. Yeah. And let me label them. This is Q1 equals to minus 6 nanocoulombs. And Q2 equals to 3 nanocoulombs. And then, of course, they create, the first charge creates its own electric field. The second charge creates its own electric field. Of course, at every point, there will be superposition of 2 fields. So let's just pick any point and find the net electric field like we did in the first recitation class. So the point is, to make our life a little bit easier, will be over here. So let me label this point as point P. So distances to that point, let's say this is B equals to 5 centimeters. Wait. And this distance, A, is 10. Okay, that's it. So we need to find the net electric field at point P. So let me write that down. So we need to find E at point P. Of course, it's E net. So, first of all, I bugged my students in the recitation classes, right? So, if you deal with the vector quantities, what do you have to introduce first of all? Coordinate system. Coordinate system must be shown, right? Where you can position at any point you want. In this case, I think the most convenient is position the origin at the point where we want to find the net electric field. I'm going to orient my coordinate system like this. Y is up, and this will be my x. Right? Again, it's your universal freedom to choose coordinate system any way you want. Okay, so now, before we start crunching numbers and start doing any calculations, draw pictures, right? Because whenever I see quite often during the semester and on the exam, if students don't draw pictures, it's 50% that there is a big disaster in the solution. Right? So draw it. You must see all those vectors in front of your eyes. Right? So first, contribution to the net electric field from the first charge. What's the direction of the electric field from the first charge? Yeah. Careful, guys, because yeah, sometimes on the exam, students kind of trying to do it fast and making some silly mistakes. Right? So of course it is negatively charged, negative charge. So electric field lines towards the negative charge. So electric field is along the line which goes through the negative charge. So this will be okay. It's a E1. So then second contribution from the positive charge. Of course, electric field lines, they start on the positive charge and go to infinity. So as a result, electric field will be that way. So electric field will be this way. So let me label it as E2. Right. So, and now since we want to find the net electric field, so parallelogram method. So this will be our E, which we want to find the net electric field. So now, like we did in the class, the strategy is like this. So first, let's find the magnitude, for example, which I did first, E1? Yeah, E2. Let's first find the magnitude of E2. Can we do it? Expression for the electric field. I didn't write it. There's so many formulas similar. Okay, essentially it's a KQ over R squared. Right? Only now I realized that something is missing. Why would you need surface of volume density? You have one single point charge. No, usually that I don't write. Actually, thanks for reminding, but actually it never came to I never thought about that, right? Yeah, we can add those. So a linear charge density, charge divided by the length, surface charge density, charge divided by the area, and volume, rho, charge divided by the volume over which that charge is distributed, right? Okay, so we can find the electric magnitude of the electric field E2. So let's start. Let me put here the first bullet. So magnitude of E2. Okay, and absolute value of Q2 divided by the distance from the charge to that point. Okay, quite often on the exam I see students manage to get negative value of the magnitudes. It cannot be, right? Magnitude of any vector is by definition, it's a positive number. So here, if we're trying to find the magnitude, so if the charge is negative, which creates the electric field, just use absolute value of the charge, right? We're trying to find magnitude. So that's why I put, you see this sign of, I'm taking just an absolute value of the charge. So then R2, what is R2? It's a distance from this charge to the point in question, which is essentially B. And of course, it must be in meters. Right? Not often, but sometimes still students making silly mistakes using wrong units. 10 to the power of minus 2 meters. Right? K we all know. Of course, value of K will be given in the formula sheet. Charge is given. Nano 10 to the power of minus 9. Quite often students ask me on the exam, what's the meaning or what's the value of n or mu or something else? At the end of the formula sheet, I attach the table where you can see the meanings of all those prefixes, right? So it's given. because it happens every exam, so I decided to add the table. Okay, so now let me use my notes. So what's the value of this? Okay. Why not screaming? Yes. It must be R2 squared. It's electric field, not electric potential, right? So this is for the electric potential, but we're trying to calculate the electric field. And the electric field is R to the power of 2. Usually experienced professors say something like this in the cases like this. I did it on purpose to see if you're following me. So I did it on purpose to see if you're following me. Yeah, but since lately we've been using electric potential, so it's a force of habit. So 1.07. Okay, I use more sig figs because it's not the final result. Right. Okay, so now let's find components, and then we're going to do exactly the same with the second vector. Find the magnitude, and then components. And then you will have two vectors presented in the component forms. How to add them up, it's a piece of cake. Right? So now let me write components, E2x and E2y. What's the y component of this vector? Everyone says that's 0? Because at the very beginning, in the first recitation class, some students were not confident, right? But usually after, by the time of the first midterm exam, everyone is confident in that. So y component, of course, 0. And this whole magnitude, it's the x component. Oops, times 10 to the power of 4 newtons per coulomb. Okay, so these are preliminary results. Let me frame them a little bit, and let's leave it alone for a few minutes. Now, let's do the same with the second, or the first vector, E1. So E sub 1, okay, absolute value of 1 charge Q1, and divided by R1 squared. This charge negative, but we're not using that minus. We're, again, trying to find the magnitude. We don't care right now about the directions. We will start taking care of the direction when we find components. Okay, so what's the value of R1? R1, it's at this distance from the charge to the point in question. So pretty much we just need to use Pythagorean theorem to find that R1. Everyone knows that, right? So R1 squared equals to A squared plus B squared. And again, don't forget it must be in meters. Wrong bracket. Okay, let me look at my notes. So what's the value? Again, if you plug it, you will get 0.431 times 10 to the power of 4 newtons per coulombs. Actually, this problem I gave on the first exam about 2 years ago. What? Measurements of A? Yeah, 10 centimeters. Yeah, guys, if something is not clear in terms of my handwriting, ask me quickly. I can easily respond, right? So don't try to hurt your eyes. So now, x component and y component. Okay, in order to find those, of course, we have to introduce one of the angles, right? So it's up to you. You can use this angle. You can use that angle. It doesn't matter which angle I used. Okay, I used this one, theta, right? Because now we'll have to decompose this vector into the x and y. Okay, so how can we find that angle? Pretty much you can use any function to find that angle. Sine, cosine. But I usually use tangent because originally opposite side was given and adjacent side is given in this right triangle. Right? You see this right triangle? So usually tangent is slightly more convenient. Tangent of theta equals to. Tangent, it's a ratio of what and what? Opposite versus adjacent, right side. So which is A versus O versus B. A over B. A over B. Okay, so of course you can take arctangent of A10, B5. Of course, I cannot calculate that value. So 63.43 degrees. Another thing, make sure that when you use your calculators, your calculator is in degrees, not in radians or some other units. Right? Another place for unnecessary mistakes. Okay, so now we can find components. E1x equals to, it will be E1 times, okay, which function do we have to use? Cosine. This is, we need to find this side which is adjacent to the given chosen angle, of course, cosine. And what do we have to add? No, easy. You know. Look, component of this x component, negative x direction. So the component is negative. Component is negative. Since we're not using a conventional angle, what is conventional angle in a vector algebra? If you use this angle from positive x-axis in a counterclockwise direction, if you use that angle, then that minus will appear automatically. But since we're not using that conventional angle because it's not convenient, I don't like those angles. Right. So since we use this angle, which is convenient in this situation, so we have to take care of pluses and minuses manually. Remember, we emphasized on that in our first two recitation classes. Right? So we have to put here minus because it's not going to appear from your calculations. Okay, so now, of course, everything is given. Angle we have, magnitude is given. So the answer is going to be minus 0.192 times 10 to the power of 4 newtons per coulombs. Later on, we introduce volts, newtons per coulombs, volts per meters, essentially the same thing. Now, y component. Of course, now it's a sine function, must be used. And is it a positive component or negative? Negative, of course, again, it's a negative component. Again, we need to put minus manually. So, and the value, so it will be minus 0.385 times 10 to the power of 4 newtons per coulombs. Okay, so that's the second preliminary step. So now we know everything about the first vector. And now the last step, we just need to add corresponding components, x components, y components, in order to find the components of the net field. So now E equals to E1 plus E2. It's in a vector form, but what, guys, something not clear? Good? Okay. At the end, I think we will find also a magnitude. Right now, I'm just writing in general in a vector form, right? Mm-hmm. But of course, in order to calculate, of course, you need to dive into the components. So E sub x, of course, it will be E1x plus E2x. We have our x components. Oh, wait, I'm not going to add them. I will use my notes. So it will be equal to 0.887 times 10 to the power of 4 newtons per coulombs. So many numbers different. That's why I told you at the very beginning, this problem is a little bit tedious. Straightforward, but somewhat tedious. So now let's do the same for the y component. E sub y equals E1y plus E2y. It's easy because this is your y component. So it's all comes from there. So it's a minus 0.385 times 10 to the power of 4 newtons per coulombs. OK, so essentially we can say this is the answer. We found components of a vector, so we can say we know everything about that vector. But question can ask, what about the magnitude? And of course, finding the magnitude at the very beginning, usually, OK, sometimes students not confident, but it's very straightforward. Pythagorean theorem, right? Pythagorean theorem, square of this plus square of that, and add them and take a square root. Because essentially what we found, so this is y, this is x, this is our vector E, and we found yeah, good. Positive and negative, yeah. So this is our E x, this is E y. So and now finding the magnitude, we just need to find the sort of magnitude of this hypotenuse. Square of this plus square of that, and taking square root. So E equals to square root of E x squared plus E y squared. And of course, the answer is going to be 9.67 times 10 to the power of 3 newtons per coulombs. Is that desk blocking you? Can you see it? OK, cool. Because I can actually lower it. Huh? Fascinating, yeah. I'm also planning to buy something like this into my office. Right, so now direction. So in order to find direction, we can introduce, for example, this angle phi. So this phi and that theta has nothing in common. So they define directions of different vectors. So tangent of phi, ratio of opposite side versus adjacent. This is our phi. Opposite side, it's a y component. Adjacent, x component. And in this case, use only absolute values. Just looking at the triangle, you need to know this length, you need to know that length in order to find that. Don't use minuses or pluses. So absolute value of opposite versus absolute value of the adjacent side. So if you do it, you will get 23.46 degrees. And which statement do we have to add? Yeah. Of course, you could have written with minus 23.46, right? It will be correct also. Or you can say below plus x's. Right. OK, so it's one of the problems from one of the previous exams. I think it was like 2 years ago. OK, so if you have any questions, ask. But since we can describe these electrical auras using either electric field or electric potential, let's also find the value of the electric potential at that point. Right, so let's just exhaust this problem completely. So I still have some space left. So now let's find V at point P. Of course, V, it's a net electric potential. So here, how much time we spent applying essentially principle of superposition. Let's just do the same, but now with the scalar quantity. So expression for the electric potential is here, right? So I didn't forget that. So let me just write it. So V equals to K Q over R. So it's a formula in general. So now let's apply it twice. So V at point P will be equal to V1 plus V2. It's a scalar quantity. We don't have to deal with components, with the directions, nothing like that. So it will be just K. Where is my charge Q? Q1 is negative, right? So, OK, let me first write in general. Q1 over R1 plus K Q2 over R2. I remember that one of the charges are negative. R1, it still is this. R2 is still that B. So it will be, OK, I can factor out K. 8.99 times 10 to the power of 9 newtons meter squared over coulomb squared. Q1 is what? Minus 6 times 10 to the power of minus 9 coulombs. R1, it's a B. 5 times 10 to the power of minus 2 meters. And then plus, what's the value of Q2? 3. And, OK, I didn't write down, but I think it's a square root of 125. Wait. I think you see what I've done? I think I've done exactly the same when I started this problem last night. All right, and then I had to correct it by looking at the picture. OK, look, what I've done wrong. R1, OK, so minus 6. It's a Q1, R1, so it's a square root of what? Square of this plus square of that. Square root of 125. That's what I need to use, not 5. So let me erase this. So it will be square root of 125 times 10 to the power of minus 2 meters. Again, exactly the same mistake I made last night when I was preparing this problem, and then I quickly realized that it's not wrong. I mean, it's not right. So then R2, it's just B, 5 times 10 to the power of minus 2 meters. OK, so the answer is yeah, of course. So the answer will be 56.7 volts. Not a small number. I'm surprised. So this 10 to the power of 9, 10 to the power of minus 9, they just cancel each other, right? So, but here we have square 10 to the power of minus 2, which will go up as 10 to the power of 2. OK, so this is the first problem. OK, any questions? A little bit tedious, yeah, but usually the first one of the problems of this type, yeah. No, first you need to find whatever. You can calculate in meters or in centimeters. So I calculated first in centimeters. So it's a square of this 100, square of this 25. So it's 125. I took a square root. So that will be in centimeters. And then I added 10 to the power of minus 2. So now it's in meters. Right. And I don't have to square because this is the electric potential. It's not the electric field like over here, r to the power of 2. It's a little bit confusing, so like I've made a mistake at the very beginning when I wrote the wrong formula. Okay. So next one, let's find the spot for an equilibrium of one charge. So what's that? So number 2. So let's say we have 2 charges on a line. So let me first draw a line. Here, let's say charge is 4q. Let's say here charge is q. Both positive, essentially. Right. I can even add plus, plus. Distance between them is L. Then there is a charge number 3. And we need to find the spot for that charge so that the net electric force acting on the charge will be 0. So is it possible if I position it here? Will I be able to find the spot where net electric force is 0, or over here or over there? So let's just first discuss in which region it's possible, and then let's actually find the distance at which it's possible. Okay, let me check if I give everything that we need. Yeah. So let me write. So let's find a position for the third charge, Q, where net force equals to 0. Okay, so what if I position that charge over here somewhere? In region, did I label it? No, just let's just discuss this region. So is it possible to find a spot where the net electric force acting on the charge is 0 in that region? Still thinking. Some people I see confident already. So let's just draw all the forces to see their directions. Essentially, here the question about the direction. So let's analyze. So this positive charge plus 4q. This is also a positive charge. So what will be the direction of the electric force that this charge exerts on that one? Of course, it's a force of repulsion, right? So let me label this charge maybe like 1. This is the charge number 1, and this is charge number 2. So first force will be, of course, force of repulsion. It will be F1. Then this charge, also positive. This is also positive. Of course, there will be force of repulsion. So the second force will be also that way to the left. And this situation is true. It doesn't matter where you position this charge Q. Here, 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 or at the infinity. All the time, these two forces will be pointing in the same direction. Is it possible for them to balance each other out? Of course not. Every time they are in the same direction. So it's impossible to find the spot where the net force would be equal to 0, right? So, make sense? For that region, of course not. Yeah, we just, essentially we have 3 regions, right? So here, region number 1, here it's a region number 2, and region number 3, right? So for that region, of course, it's impossible which way I wrote it. So sum of forces is not 0. Impossible. Here it's impossible. So now let's do the same, for example, for this region number 3. And now, are you still not sure? OK. So now, for this region, still thinking? Impossible? Of course, yeah. I mean, it's, of course, impossible. The same situation, right? This charge still going to repel F1. And this charge, again, going to do the same, F2. So in the same directions, of course, the net, it's impossible to balance these two forces. So sum of all forces is not equal to 0. Also impossible. So now let's analyze this region, number 2. So what if I position my charge over here? And let's do the same. So this charge is going to repel that charge that way. So this will be F1. And then this charge is going to repel that one. Of course, it's opposite direction. So this will be F2. Directions are opposite, so it feels like we should be able to find the spot where the net force equals to 0. Right? So it is possible here. So now we just need to actually calculate that spot. So let's introduce an unknown. Essentially, unknown, it's a distance. Let's say distance from this charge to that one is x, our unknown, which we want to find. Then, of course, distance from that charge to this one will be L minus x, because the total distance is L. So, of course, this will be L minus x. So now let's just write down expression for both of these forces and equate them, essentially. Right? So let me write region number 2. Right, so that one. OK, I use Roman 2. So it means F1 equals to F2. Coulomb's law, 2-point charges. So we just need to write it twice. F1, it's between 4Q and Q. So it will be K 4Q times Q, and divided by the distance. Distance is unknown x. Yeah, I introduced that x, yeah. So divided by x squared. So, and F2 will be very similar, but now it will be K, Q, Q, divided by L minus x squared. Simple equation with one unknown. Let's just solve it. So it's not a rocket science. Of course, K can be cancelled. Q squared also will be cancelled. So as a result, we will have 1. OK, not 1. It's 4 divided by x squared equals to 1 over L minus x squared. We can take square root of both sides. So it will be 2 over x equals to 1 over L minus x. It's a 1. Upstairs, it's 1. It's not L. So simple proportion. So it will be 2L minus x equals to x. Just multiply this by that and this by that. So it will be 2L, OK, yeah, 2L equals to x plus 2x. Just move that x to that side with 2. And so it's a 3x. And as a result, x equals to 2/3 of an L. Let me check with my answer. Yeah. a little bit of thinking, and then you write down one equation and solve it for an unknown. Yeah. Yeah. Every time in the problems like this, you need to introduce your unknown.
So you have to put it in the thing because you need to know where the x is.
Yes, yes, you need to introduce that. Assume sort of you pick an arbitrary position with some arbitrary distance x, and then write the equation, and from that equation that unknown can be found. It's a classical. Of course, it doesn't matter if you introduce this x or that x. If this is x, this will be L minus x. And of course, the answer will be 1 over 3x or something like that. 1 over 3L. Because in that case, your x will be different, right? Distance. Yeah? No. Variables, at this point, you should be able to introduce the variables, right? So, so far, I never gave a problem like this, right? So, but you need to be exposed to the problems like this, and you have you must have skills of setting up these equations, right? Writing down. So, it's a slowly, that's what education does, right? So first you see it for the first time, then, and you're surprised. Then you see for the second time, you're kind of more or less familiar, and essentially, of course, you will feel comfortable, right? So setting up the problems like this. So now let's answer a few conceptual questions just to relax a little bit. Okay, can I start erasing this? Mm-hmm. So, number 3, and here there will be just a few several times something like this I gave on among multiple choice questions. And let's do this one more time. So let's say this is the square. So it's a square. And let's position a few charges. At this corner, minus q. This corner, minus q. Here also, minus q. And over here, plus q. I can even maybe label like this is charge 1, this is charge 2, this is 3, and this is 4. And so we're interested at the center. Okay, at the center there is no charge, it's just a point in space. So first, let's find E direction. E net at the center. And also V net at the center. So let's just, electric field, I just want to find the direction. I don't want to calculate numbers because we've done that already in the first problem. It's enough. Okay, so let's just start drawing vectors. Again, remembering that this is square, and essentially this distance, let's say L, between the charge and the center, let's say this distance also L, this L, and that L. So, lots of symmetry. So let's start drawing vectors. So the charge 1, direction of the electric field produced by this charge 1 at this point. Of course, it will be away from the charge, right? So basically along this diagonal line, right? So this will be E1. Then, second, it's a negative charge. Of course, electric field will be towards the negative charge. Again, along this, now along this diagonal line. So it will be this E2. Then, charge 3, it's a negative charge. And of course, all these vectors are of the same magnitude because the values of the charge is the same, distances are the same. So of course, magnitudes are going to be the same. Of course, directions are different, but magnitudes are the same. Then charge 3, it's a negative charge. So it will be, negative. So it should be towards that charge. So this will be E sub 3. And the last one, negative charge, again, it must be toward that charge of the same magnitude. So E sub 4. OK, once you drew them, now you start thinking, what happens with the electric field contribution from the charge 2 and the charge 4? They cancel. So pretty much here you need to look at the symmetry, right? So you don't need to guess, it's quite straightforward. First draw them, remembering that magnitudes are the same. So magnitude of this equals to the magnitude of that, and directions are opposite. Of course, they're going to cancel each other. So this gets canceled by that. But these two vectors of the same magnitude in the same direction, so of course, if you add them up, you're going to get the net electric field pointing this way, so doubling. So it will be E net equals to E essentially 1 plus E3. OK? Because, yeah, quite often I use this idea in the clicker questions for our lectures or for the exams sometimes. OK, so that's the electric field. Now, electric potential. Now, electric potential. So, electric potential now, V net, it will be, of course, V1 plus V2 plus V3 and plus V4. Again, principle of superposition, but now for this scalar quantity. OK, good, guys? OK, cool. So now this, of course, will be K, the first charge positive, so it's a plus Q over L. We assume distance L is given for simplicity. So the second charge, 2, is negative, so it will be plus K minus Q over L. Then third charge also negative, plus K minus Q over L. And the charge number 4 also negative. So the first two guys, again, like in this case, of course, they cancel each other. And as a result, we have only two negative components at the end, which add each other. So it will be minus 2kq over L. Right. OK, enough. All right, so playing with this electric field, electric force. Electric field, electric potential, not force. Actually, a previous problem was about the force. OK? Yeah. Let me then erase it. And now let's start moving. Probably let's first discuss properties of conductors and then Gauss's law. Yeah. So after that, there will be, after Gauss's law, there will be two problems about motion of point charges. OK, we'll see. So number 4. So now conductors. Okay, so let's assume that we have this piece of a conductor. And let me create a couple of holes. And the conductor is here. So now let's dump a few charges. Negative charge over here, minus 2 coulombs. In this hole, let's assume that there are 2 charges. One is minus 3 coulombs, and this is positive, let's say plus 8 coulombs. No, first I looked, it looks like a traffic light. One additional color is missing, but for traffic light, it's a different slightly colors. Red, yellow, and green. Okay, you remember we solve the problems of this type. So I guess you know what will be the questions. So let's find the net charge on this internal surface, net charge on this interior surface, and the amount of charge on the external surface, on the outer surface. Let's find all those charges. So let me write. So let's find, let me label this surface as, okay, the amount of charge on this surface is QI1, surface number 1, and this, let's say, QI internal or interior surface. I stands for interior or internal. And surface number 2. And exterior, of course, will be over here. Q out, outer surface. So essentially, that's what we need to find. Question mark, and question mark. We've solved something like this. Okay, so find those charges. So now let's start with Q interior of the first surface. What will be the amount of charge on the interior surface number 1? Yeah, plus 2 coulombs. Right. Again, if you want to prove it, of course, you have to use Gauss's law. Pick the Gaussian surface just above that surface, right? So flux will be 0, and since we have a charge inside, and in order to make the net charge 0, there must be charge of an opposite side of the same absolute value, but on the surface, right? So yes. Every time we assume that, okay, conductor in electrostatic equilibrium. Let's say this way, I'm not crazy to expose you to some to those periods or moments of time when the conductor is not in electrostatic equilibrium. Yeah, whenever in the problem, of course, I will actually write it's an electrostatic equilibrium, right? So, if it's not written, usually it is assumed. So, yeah, as you said, it's absolutely correct. So it will be plus 2 coulombs. So pretty much, if you write the answer, of course, I will buy it because it's obvious. So now, what about the, yeah, of course, distribution of that charge can be complicated. It depends on the shape of the hole. It depends where this charge is relative to the surface. So distribution is complicated. I will never, we'll never discuss that. But we're talking about the total amount of charge, which is somehow distributed over the surface. And we can tell that it will be equal to plus 2 coulombs. So now this surface, I2, now we have 2 charges inside. So positive charge is going to induce negative charges on the surface. Negative charge is going to induce positive charges on the surface. So there will be some balancing, right? And so we can just find the net charge in the hole. Net charge in the hole, it will be what? Plus 8 minus 3, it will be plus 5. So it means that on the interior surface, there will be minus 5 coulomb of the charge, right? So positive charge net inside, so on the interior surface will be negative. So it will be minus 8 coulombs minus 3 coulombs. So it's minus 5 coulombs, right? So it will be negative charge induced on this interior surface. So I can draw a bunch of minuses. And on that surface, it's positive, positively charged. Okay, and so now final question. What about the surface on the amount of charge on the outer surface? Conservation of charge. In this case, 3 rooms, right? Room number 1, room number 2, and room number 3 isolated from the world. If there are 10 people in 3 rooms, so if there are 2 and 3 in the first 2 rooms, then there must be 5 people in the last room, right? So idea is very simple. Conservation of charge. Conservation of charge. Of course, of the conductor or in the conductor. So it will be Q total. I didn't give you one last piece. Now, when I got to this point, I realized what is missing. Total charge of the conductor, right? Of course, I can say, let's assume it's electrically neutral, but it's too boring. Let's assume something, right? Okay, net charge minus 6 coulombs. Okay, why not? So let's assume Q total equals to minus 6 coulombs. Let's assume that, given. So Q total equals to Q in the 1 plus QI2 and plus Q on the outer surface. So given, found, unknown. Piece of cake, right? So let's just solve it for Q out. So Q on the outer surface equals Q total minus QI1 minus QI2. At this point, be careful, because I see sometimes students know what they do, but when they start calculating, and quite often they forget about these minuses. So minus can be from the expression, minus from the value of the charge. As a result, you can supposed to get a positive number, but sometimes students sort of start skipping steps. As a result, start losing minuses and start giving some wrong answers. And then when they come to my office, damn it, you understand that I understood what I was doing. Be careful. So Q total is minus 6 coulombs, then minus from the expression, and internal surfaces on this surface minus 2. Then minus from the expression, and this charge is negative, minus 5 coulombs. So minus and minus. So it will be positive. And so what are we getting? Minus 8 plus 5, negative 3. Right? So Q out equals to minus 3 coulombs. Usually a problem like this is among multiple choice questions, because usually it requires like 1 or 2 minutes to solve it. It doesn't need a significant effort. Okay, I feel like I need to change this marker. Losing contrast. Any questions? Okay, let's move. Now, flux and Gauss's law. Uh, okay, conceptual questions. Then I will erase them and continue with the Gauss's law. So what if we have CQ conceptual question? What if we have a surface like this and charge over here, let's say plus Q? Of course, this positive charge creates the electric field lines. We can draw them. They look nice. So there are electric field lines. There is a surface. Of course, we can talk about the electric flux. Because you remember flux, electric flux is a number of electric field lines crossing a surface. Right? So what's the electric flux through this surface? The electric flux through that surface. Any ideas? Yeah. Yes, that's by definition okay. Although this cannot be used because if electric field is not uniform and surface is not flat. It's a cylindrical essentially surface, right? So we discussed something like this in our in the lecture. And since it's been a while, so you started forgetting about that the second time. Do you remember? No? Questions like this are quite possible on the exam. Actually, almost every exam I give something like this, right? All right. No, guys. Right. Yeah, that's why we actually have an exam review session, right, to refresh. Because, yeah, this is some fundamental idea which usually, still thinking? Yeah, it's a closed surface. It's a, but it's a good question, good point. It's a closed surface, cylindrical surface. You wanted to say something, right? Never mind, change your mind, right? Okay, guys. Yeah. No, you. Yeah. Okay. Yeah, you can do that, right? But there is an easier way. Way easier way. Okay, guys, it's enough of me torturing you. But again, since it's good sometimes to torture students because then they will remember it better. Sorry, don't tell it to anyone. It's not educational approach, right? So, who said something? No? Girls? E dot dA. Again, you're trying to, yes, it's a by definition, that's what Gauss's law. Okay. What is this? Integral area, it's all correct. So what the whole structure, all the structure? It's written. It's electric flux, right? In the Gauss's law, on the left-hand side, we have the electric flux. And any Gaussian surface can be used. Any. You can even pick a Gaussian surface in a black hole. It will be still correct to use Gauss's law. Can we use it over here, Gauss's law? So this will be flux over this cylinder, right? And on the left-hand side, that flux equals to Q enclosed over epsilon naught. Look inside of the cylinder. Are there any charges? Of course, zero charges, you see? Zero charge inside. So 0 divided by epsilon naught is 0. So the total flux through that cylinder will be 0. If I asked you about the electric field on that cylinder or the Gaussian surface, of course you would have to dive into that EDA cosine and struggle and suffer, but I'm not that bad, because you will here struggle a lot, right? So you will not be able to finish it in the whole exam, right? But I asked about the electric flux, right? So as a result, the answer is immediate, right? So you look inside, what's the total amount of charge inside? Take that amount of charge, divide it by epsilon naught, and that's the value of the electric flux. In this case, charge is 0, because there are no any charges inside, so the flux will be 0. So what does it mean, 0 flux? It doesn't mean that none of the electric field lines crossing the surface. It just means that we have equal number of electric field lines entering the surface and exiting. When they enter, they give us negative flux. When they exit, they give us positive flux. Positive, negative gives you net 0 flux, right? Okay, so, okay, let me write. So Gauss's law. Okay, let me write. Use Gauss's law. So integral of E dot dA, but we don't need this, right? So essentially, it's a Q enclosed over epsilon naught. So essentially, it's these sides. Flux equals to 0. Q enclosed is 0. Equals to 0. So no charge inside. Okay, so now after this you will remember for some time. So now let's make slightly different situation. Lack of imagination, I created another surface like this, exactly the same. And now let me dump a few charges. So plus Q. Then over here I will dump plus Q, and over here there will be a minus Q. The same question. What's the electric flux through this, again, surface? Of course, now you all see what's the answer, right? Plus Q minus Q, total charge inside is 0, divided by epsilon naught, flux will be 0. So, okay, good. So flux equals to, again, Q enclosed over epsilon naught. So it's a plus Q minus Q. But of course, if there will be net charge not 0, divide that charge by epsilon naught, and that will be the value of the flux, electric flux. Again, number of electric field lines, physical meaning of that quantity. Number of the electric field lines crossing the surface. Okay, maybe I will not draw. I will not draw anything on the picture, or maybe I will draw. Okay, so after this, I was planning to move to Gauss's law, but then I realized there is another problem about the conductors in electrostatic equilibrium. So what if we have metal sphere? Right, and let's say we have two charges, I don't know, over here Q1 and over here Q2. I don't know, maybe one is positive, one is negative, for example. Why not? So what's the net electric field inside of that sphere? 0. Okay, good. So good. So I can erase this. I was surprised a little bit about the flux, but since we discussed these questions usually, like I think about a month ago, so you forgot about that. Okay, so now let's actually find the electric field using Gauss's law, because finding electric flux, again, guys, be careful. If the question about the electric flux, usually then the answer is reasonably straightforward. Right? So again, net charge divided by epsilon naught. But if the question about finding electric field, then of course you need to dive into the electric field, area vector, and so on and so forth. So let's, again, since we've done it a month ago, let's solve one problem. to refresh, just to refresh. Because again, as I promised to you, usually almost every semester I give a problem about Gauss's law on the exam. And we have only two types of symmetries, spherical, cylindrical. Just practice it at home, so you should be able, and you should be fine after that. So this, let me call it 6. Numbers must grow, right? Inflation. All right. So let's assume that we have a non-conducting charged sphere. Non-conducting, uniformly, of course, uniformly. Okay, not sphere, sorry, charged shell. Okay, let me draw it. It's good for Friday evening, right? So that will be outer surface, and now let's say this will be our inner surface. Okay, radii. A, B. So this is a hole. So nothing inside of this. So let me emphasize, it's a hole. So the material is here. And on purpose, you see I wrote non-conducting. Do not assume properties of, do not use properties of conductors over here. Because almost every semester, a few students write, electric field inside is 0. No, that's only correct if you have a conductor and tons of free electrons. In this case, I don't know, it's some shell stuffed with charges, right? Stuffed with electrons, but they're not free. Or some other charges. So, and it's uniformly charged. So it means that I can draw these pluses with more or less uniform density. So the total charge is given. So let me write what is given. Q, let's assume it's positive, radii A and B. So that's what is given. And I want to pick the most complicated part of the problem, and let's find the electric field in the shell. Because finding electric field in the hole, actually, what will be the electric field in the hole using Gauss's law? 0? Again, yeah. So imagine applying Gauss's law for the Gaussian surface which is inside. What will be the Q enclosed? 0. There's no any charges inside. So Q enclosed is 0. Of course, electric field will be 0. Okay. So finding electric field over here will be trivial. So let's find the electric field in the shell. So let's find electric field. Okay, for R larger than A or equal and less or equal than B in the shell. Okay, essentially steps are, since the same spherical symmetry, steps are going to be exactly the same like I did in my lectures, in our lectures, right? So let me just quickly fly through those steps just to review. Again, because this is the review session. So first of all, of course, we need to write Gauss's law. You need to show what you're planning to use. It's just a nice habit. And the first step which you have to make before you start applying Gauss's law, you need to pick a Gaussian surface, because without Gaussian surface you wouldn't be able to move any further. You'll get stuck. You have to integrate over that surface. You need to see which charges are inside. Gaussian surface must be picked. Okay, again, you can use any Gaussian surface your soul desires, but of course you have to be smart or wise, and you need to solve the problem, so you need to pick the best possible. Right? So the best surface, of course, is concentric with our shell, right, and between A and B of some arbitrary radius r. Okay, so that's my Gaussian surface. Right. And so now, after this, we can start evaluating integral. And that's where usually students are skipping tons of steps most of the time. And I feel kind of I don't want to punish much for that. And it's a dilemma. So, but anyway, let me show how I do it. And of course, you saw it in the lecture. Okay, so first of all, of course, every time I demand from students, show electric field vector and area vector. It must be shown in the picture. So, electric field vector, because of the symmetry, spherical symmetry. Again, I'm not going to justify it this time. I did it in the lecture. So, of course, electric field will be radial towards the outside, essentially. Okay, that way, because it's a positively charged sphere. All right, so the electric field will be this way. Right, so E. And you see, I usually draw it on the Gaussian surface, because next to that, I will draw area vector. And so we want to see their mutual orientation. So I usually try to draw them next to each other. Or over here, I can also draw electric field. So then, area vector. Of course, area vector must be positioned right next to the Gaussian surface. Don't draw it somewhere else, because it's kind of, I cannot say it's absolutely wrong, because you can grab a vector and move it anywhere you want if you preserve its magnitude and direction. So strictly speaking, you can position that vector anywhere you want, but it's not right. You're supposed to show it next to the Gaussian surface. So let's pick that small patch. So this will be dA. Again, you remember convention for the Gaussian surface, area vector must point towards the outside. Right? It's convention. Then if you take this patch, so this will be again dA. Or if we take this patch, this will be our dA. Again, we just need to see their mutual orientation. In this case, they are parallel to each other, obviously. Yeah? Not barely smaller. In this case, it's some arbitrary radius r, but r is between A and B. In the limits, it can be equal to A, it can be equal to B, it can be close to B, it can be close to A, it can be at any radius between A and B. Right? So essentially, in this case, r is a variable, because at the end, we're going to get a function. Right? It's sort of from the same song, like, you remember when we were balancing forces, and you were asking me, so how should we introduce that x? Are you going to give us x? It's the same problem. You need to introduce some variable into the problem. Write down the equation and then solve it and get a function of some particular values. Right? It's sort of the same here. You need to introduce a variable. And usually, it's between the limits. If you have some region, it's this limit, that limit, your variable is between. It's a variable. Okay, so now, first explanation box. So we can see that electric field and the area vector are parallel to each other. It means that the angle between them is 0 degrees, and dot product can be simplified. Right? So we can have E dot dA. It is equal to E dA times cosine of 0 degrees. I just wrote down explicitly dot product. And you see, cosine of 0 degrees is 1. So as a result, we have just a product of magnitudes left. It's not a dot product. It's just a product of two magnitudes, two positive values. So directions disappeared. So now, of course, I can rewrite it as integral of E dA, of course, over the same Gaussian surface. Again, what's the major difference? Product of vectors, two vectors. Now it's a product of two absolute values of those vectors. So now, at that point, we don't care about the directions of the vectors. And that's the achievement of the first step. OK, so now, second, since electric field, obviously, because of the symmetry and because the way we pick the Gaussian surface, we can say that electric field, obviously, is exactly the same at any point of this Gaussian surface. Again, I justified it in the lecture. Now we're refreshing it. E is constant on the Gaussian surface. Sometimes I see students write uniform. It's not uniform. Uniform, it's exactly the same at every point, direction the same, but in our case, directions are different. And if you step away from the Gaussian surface this way or that way, electric field will be different. So it's not uniform. And of course, I usually don't subtract points for that, but strictly speaking, it's not correct. It's a constant on the Gaussian surface. Since we are wise, smart, we pick the best surface, and we can use milk the symmetry of this problem, right? Essentially. OK, so now, since it's a constant, we can extract it from the sign of integration. Any constant can be extracted from the sign of integration because, again, integration is done over the Gaussian surface, where E is constant. Any constant factor can be extracted from the sign of integration. So it will be E integral over dA, again, over the Gaussian surface. And again, strictly speaking, it's still calculus 3 integral. Some of you probably are taking that course right now. But you know the answer. And of course, that is just the area of the Gaussian surface. Don't use the surface of external or internal, that surface, Gaussian surface. So it's and at this point, still maybe like 20% of students use the wrong formulas. It's not the circumference, it's not the volume, it's the area of the sphere, guys. And at the end of the formula sheet, because it happens from semester to semester, so I decided to add those formulas. So just look at the end of the formula sheet, right? So area of the surface, 4 pi r squared, r small, right? So it's a 4 pi r squared. And again, when I was sitting and grading, it's a big dilemma. It's obviously a silly mistake, but still kind of mistake. It is serious, but usually try to be nice, right? And OK, so the flux, electric flux. And according to the Gauss's law, it must be equal to enclosed charge divided by epsilon naught. And again, I've warned you during the lecture and doing it again. After this, usually I asked, find Q enclosed. And maybe like 10–15% of students, even more, they just solve this equation for Q enclosed, basically in terms of E, and claim this is the Q enclosed. No, no, no. This is our sort of local unknown. This is our global unknown in the problem. So don't try to write the answer, not the answer. This unknown in terms of your global unknown. Again, it's not wrong. It's just useless completely. It doesn't give us anything in terms of solution, right? So when I see students write like that, it's essentially 0, right? I mean, not 0 for the whole problem, but for that particular part, right? So Q enclosed now should be found using sort of a definition of Q enclosed. It's the total amount of charge which is physically present inside of the Gaussian surface. That's it. So first of all, let's look on the picture where that Q enclosed. Inside of the Gaussian surface is here, so it's a discharge. In the hole, there are no any charges. So it's between this surface and that surface. So let me highlight it somehow. So that's our Q enclosed. OK, let me show it here somewhere. The total charge Q is between sphere with radius a and sphere with radius b. Our charge Q enclosed, of course, smaller than that Q. So, of course, it will be some kind of portion of that Q capital, right? Okay, so let's start finding it. And this part, finding Q enclosed, is all about this formula, which you asked me to write. So it's all here, nothing else. Definition of Q, definition of volume charge density. It's the total charge, whatever charge you use, divided by the volume over which that particular charge is distributed. So you can use Q enclosed divided by the volume over Q enclosed distributed. You can use total charge divided by the total volume over which total charge is distributed. You can use any charge, portion of the charge. But of course, every time you need to divide it by the volume over which that particular charge is distributed. These formulas, as I said, I never felt like a need to write these formulas, but I will think. You can write when you get to the exam. You can write. You have to write all as much as you can write when you get on the exam. Right. Again, what surprises me, if I ask you about mass density, everyone is comfortable answering that question. But when about charge density, students start panicking. Right? So I don't know why. Some psychological issue. Right? So that's why I decided to give at some point, started giving that quiz, take-home quiz about charge density. Because again, as I keep saying, you shouldn't be having troubles over this. Okay, we'll see about this. Right? So anyway, let me write. So it's all about this formula. And, okay, let me even frame. So it's a. So let's first find volume charge density in this case. So can we find it? Let's use the total charge, which is given essentially in the problem, right? So we take a total charge and divide it by which volume? What do you mean by total volume? Yeah, we need to subtract the whole every time because that our total charge Q is distributed in this shell. Whole is empty. So, and of course you remember, so you need to subtract volumes. Do not subtract radii and then cube it and then raise it to the power of 3 because I see it almost every semester, right? Okay, it's strange, right? So essentially, I know, a cube, it's a, no, b. B cube minus a cube is not equal to b minus a to the power of 3. So these are two different things. We're subtracting volumes. So of course, it will be something like that. Of course, there will be some additional factor. Okay, anyway, so let me erase this. So it will be a volume of the sphere with radius r Gaussian. Sorry, I'm jumping ahead. So it's a volume with the sphere of the sphere with radius b minus volume of the whole. Again, volumes of the sphere are given in the formula sheet. So it will be Q divided by 4 pi over 3, and it will be b to the power of 3 minus a to the power of 3. Okay, that's it. So now let's find Q enclosed. Again, look at this formula. So now we need to find Q. Basically, you apply this formula for Q enclosed. So essentially, Q enclosed divided by the volume over which Q enclosed is distributed. But now we need to find it, so you just need to solve it for Q. Q equals rho times V. So rho, which we just found because it's exactly the same charge is distributed uniformly, so charge density is the same, so we can use it to find any charge we want now. So take rho and multiply by the volume over which enclosed charge is distributed. So now it will be what? How should I label it? Volume of, I don't know, between R and A. Or maybe I can just write R and A. Subscript R and subscript A. Ra. Okay, so it's a volume charge density. Okay, I just can rewrite it. So it will be 4 pi over 3 b cube minus a cube. So it's just a rho. And now times this volume. So again, it's the volume with the volume of this sphere with radius r small, right? Minus whole volume of the sphere with radius a. Again, like over here, subtracting the whole, because the whole is empty. Okay. So finally, so it will be q over 4 pi over 3 So 4 pi over 3 will be cancelled, and we're getting the formula. So Q and ratio of this, and this crazy ratio. So usually in the problems like this, the largest number of mistakes in these two lines. At least, I don't know, 30 or 40% mistakes over here. Although, from the point of view of physics, idea of charge density, volume, I don't know, volume charge density or linear surface, one of the easiest, right? So Gauss is a little more complicated. Okay, so let's finally write down the answer. So back to this. So this should be inserted into what we left over there. And let's finally write down the result. E times, so I'm just rewriting this 4 pi r squared equals to essentially that q divided by epsilon naught and the ratio of those cubes. Almost done. So E as a function of r, it's a function, q divided by 4 pi epsilon naught, r squared. Yeah. 4 pi epsilon naught r cube minus a cube, b cube minus a cube, every time subtracting a cube. R squared, it's this one. You see, I just moved this r squared there downstairs. Lots of symbols to write, but you guys are science majors. If you were a psychologist or philosophers, then you will have to use lots of words. So people would be falling asleep from your words here, you're falling asleep from symbols. Okay, so of course it's possible I can make this problem, for example, slightly more complicated. What if I add, for example, some point charge at the center? What will be the different? What will be, how different the problem will be? Would be? Huh? Yeah, there will be charge. Of course, it will be different. So how would this solution be different? Essentially, this part will be exactly the same. Essentially, the symmetry is the same. So pretty much up to this point, everything will be the same. So then Q enclosed. How Q enclosed will be different? Exactly. We just need to add over here additional charge. That charge at the center will be Q plus all this mass. That's it. Essentially, it's exactly the same solution, exactly the same problem, but now you just add additional charge because you just need to count all the charges physically inside. All this mass we already took care, but if there is over here charge at the center, just add it. So Q plus that Q enclosed, which is over here. That's it. It's essentially the same problem. Whew. Again, my impressions or emotions when, again, I was like you, undergrad level student. Actually, we like these problems because once you get the idea, it's a question just of getting through this, right? It's not a rocket science. Of course, it's difficult to sort of, I don't know, embrace what's the physical meaning of this Gauss's law. Sounds so, but it's a fundamental equation, right? So which we take as an axiom essentially. But then, and then the rest is just a mechanical application of what you know. Whew. So what about time? Getting close to 2 hours. Okay, now, you know what, another conceptual question, CQ. I don't need much space for that question. And then we will start solving the problem, different problem. Okay, anyway, any questions about this? So, quite often I give problems of this type, questions. What if we have, for example, I don't know, some negative charge, minus Q, capital. And let's say we have some electron traveling like this. So it's an electron. Can you see direction of trajectory? So initial point, final point. So we need to answer the question, what happens with the potential energy of the system? So what's the dynamics of the potential energy? Potential energy. Is it increasing? Is it decreasing? Is it stays the same, right? So essentially that question, right? So what happens with the potential energy as the electron travels along this trajectory? So I need to analyze. Of course, I can look at my notes, right? So first of all, let's grab the formula which actually describes potential energy of 2-point charges. Don't use the wrong formula. So 2-point charges, it's not this. It's a charge inside of the uniform electric field. It's this one, potential energy of 2-point charges, and that's what our system is. So KQQ over R. Let's just rewrite it. U equals K, Q small times Q capital over R, distance between them. So, is the potential energy positive or negative? Positive? No, it doesn't matter, right? So you just need to look, in order to find out what's the sign of the potential energy, it depends only on what? Charges. Are they positive or negative? If they're both positive, potential energy is going to be positive because R cannot be negative. Basically, R, it's a, R in polar coordinates. It's between 0 and infinity. R cannot be negative. So it's the sign of the U is in the product of these two charges. In our case, both charges are negative, so the potential energy is going to be positive, right? So potential energy is positive. Right. Again, so since this is negative, this is also negative. Too much of negativity gives you positive. Okay, so then next step, now you need to analyze what happens with R, and as a result, what is the effect of R on U. So what happens with R as an electron travels? Yeah, so this is the R. So of course it's getting smaller because electrons getting closer and closer to the, okay, probably I should have curved it a little bit more because here it looks like distance is larger than over there. Okay, I can make it shorter. So this will be my final point. All right. All right, so R is getting smaller, so R getting smaller, right? So if R getting smaller, and since it is in the denominator, so it means that potential energy is getting larger, right? So U is growing in time. Oops. So let me check. Positive potential energy becomes more positive here. Again, we had a clicker question similar to this, but in that case we had a negative potential energy, right? And our negative potential energy was becoming more negative, but here positive becoming more positive. So it depends on the situation, right? So, but that's how we should analyze it. Okay, cool. Again, since we've done it, so now we just refreshed it. Whew. All right, so now next, solve problems about motion of charges in a uniform or not uniform electric field. You remember we solved the problems like this, finding velocity, position, traveling time. Let's refresh that. And of course, there will be two problems. In one, point charge will be exposed to the uniform electric field, and the second, 2-point charges. And after that, essentially, yeah, and after that, there will be a little bit of these transitions between the electric field and the electric potential, and we'll call it a day. So it will be about 3 hours. And again, sometimes students send me emails, how should I prepare myself better for the exam? Essentially, again, what I did, so when I was a student, I would first look through all the lectures, what was discussed, right? So I will be familiar. Then, of course, I would look at the examples which were in the lectures. Then I will look through all the homeworks, right? So make sure that I can solve them by myself without having anything in front of me. All right, and then of course recitation classes, because again all the exam problems are somewhat similar to what we had in the past, right? So if you know how to do that, you should be able to ace the exam. If you cannot still ace the exam, instructor is too tough. Or it means that you are in Caltech, right, in the California Institute of Technology, right? I heard that that is a pressure cooker. Like my advisor usually used to say, it's probably one of the best physics schools in the country, at least in his opinion. Caltech, yeah. Undergraduate school, the best, one of the best undergraduate, the best. It's in his opinion, of course. Okay, so now, next one, let me change the number, 7. Okay, electron. Electron is going to fly inside of the capacitor. So essentially, it will be this system. Right? So let me write. Okay. Electron inside of a parallel plate capacitor. EP capacitor. Whenever I say it, it reminds me that sitcom Everybody Loves Raymond. Maybe you've seen it. In one of the episodes, he was in his high school. He was called like PP Raymond for an accident. So whenever I say PP capacitor, it reminds me of that episode. Sorry, I didn't tell you anything. Okay. So, capacitor. All right, and you know what? We're going to shoot electron because without that, electron would not be able to move. So it means that where is the electron? Near which plate? Near positively charged plate. All right. In that case, by itself, it will never fly. So let's assume that. So let's assume that this is the positive electrode. That is negative. Right. And our electron first is here, Q. Okay, you know what? Let me use E negative symbol. Right. E minus. Right. And so, essentially, the problem is, let me give you some numbers. So the spacing between the plates, 1 centimeter. Wow, it's a big distance, 1 centimeter. Then potential difference between the electrodes. Of course, it's a V plus minus V minus, and that number is 10 kilovolts. So you connected battery or power supply to the plates, so 10 kilovolts potential difference. So now situation. So you essentially want to find the correct initial speed of the electron so that if you shoot that electron with that speed, it will just barely reach the negative electrode. Basically, the final velocity of the electrode before it is going to hit the electrode must be negative. Oh, it must be 0. Sorry, must be 0. Right? So you need to find initial velocity so that the electron would just reach the negative electrode with 0 final speed. So this will be the trajectory. And so this is initial point. This is the final point. And essentially, we want V final to be 0. Your boss gave you an assignment, right? So assign it so that, design it so that it will just barely reach that point. So, and the question is, we need to find this V initial. So we need to find V initial so that V final is 0 near the negative electrode. So let me check if I gave you everything, because once I forgot something. D delta V, initial velocity. Okay. How many approaches do we have to solve problems of this type? 2, right? So we can use energies with the conservation of mechanical energy, or we can use forces using forces, accelerations, and then kinematic equations. So let's just use, again, both of them, right? Okay, so I will start with energy. Okay, let's start energy approach. And on the exam, I usually ask for a particular method. Right, so if you don't use other methods, because in that case, at least 50% of the points will be subtracted. Strictly speaking, it's legitimately to give 0. If instructor asks for a certain method and you use a different method, so strictly speaking, it's not cheating, but we usually subtract at 50%. So energy approach, let's use that. So since force, electric force, is a conservative force, there are no any losses. So instead of, we can introduce potential energy, and then in collaboration with kinetic energy, we can use conservation of mechanical energy. So typical standard approach. Usually students have no troubles, most of the students have no troubles at all applying this method. But since it's a review, so let's solve one of the problems. So classical beginning, and now you need to dive deeper and deeper and deeper until you will see all the quantities which are given and which needs to be found. So let's do it step by step. So first, of course, it's a kinetic energy plus potential at the initial moment of time, kinetic plus potential at the final moment of time. Of course, kinetic energies, we know the expressions, right? Usually no troubles, right? 1 over 2 mv squared. So which kinetic energy, okay, any terms which are zeros, which we can remove. Final kinetic energy is 0 because that's what we want. It's our desire, our goal, right? So we want V final to be 0. So of course, final kinetic energy will be 0. Okay, so now, of course, we can write expression for the potential energy. Charge essentially given, right? But do we have to do it? Write use this formula. Of course, yeah, we can find, for example, electric field, because potential difference is given. We should be able to find electric field. But it will be additional step. What if we just use relationship between the electric potential and potential energy, and potential difference is given? So let's just use this instead of that. Because if you use this, in that case, you will have to make an additional step, and you will have to find the electric field from the potential difference. Again, it's very simple, right? Because potential difference is an electric field times the distance between the electrodes. Again, both methods can be used. So, but here, somewhat easier, slightly easier. If we just write potential energy, it's as a Q, charge of an electron, times the electric potential. Okay, so now let me rewrite it. We need to find what? Velocity. Initial, yeah. So let me move that potential energy to that side. So it will be 1 over 2 mv initial squared equals to u final minus u initial. I just moved first potential energy to that side with minus. And now let me use that formula, of course. Q, of course, the same. We can factor it out. So it will be Q v final minus v initial. And now you need to be careful with signs and which point is final, which point is initial. Look, final point is here, right? So this is our V final. This, oh, it's a V initial. This is V final. So that difference, V final minus V initial, is it positive or negative? So actually, what is the electric potential at the initial point? What's the value of the electric potential at the initial point at the negative electrode? That's the reference point. You remember the expression for the electric potential inside of the capacitor. E times x. X is the distance from what? From the negative electrode. It's your quiz, the last quiz which we had like a few days ago, right? So it's a E times x. In this case, x is 0, so the electric potential initial or final is 0. So this is 0. So this is our reference point. So This is 0, and as a result, essentially it's a delta V, our delta V, right? Let me write it like this. So it will be Q, V final, it's a V minus, minus V plus, right? And what is given? V plus minus V minus. As a result, this is minus delta V, minus delta V. So essentially, this is minus delta V, which is given. So Q times minus delta V. Now immediately the question, look, on this side we have kinetic energy. On this side we have minus Q delta V. Are we getting negative kinetic energy? Because negative kinetic energy is kind of what? Kinetic energy cannot be negative. It's either 0 or positive value. So are we getting negative value or not? No, charge is negative. Electron is negative. Right. Good, good. So it's negative also. So it will be equal to minus absolute value of the charge minus delta V. So it will be Q times delta V. So it's a positive value. So we're good. So now, essentially, we just need to look at these two ends and solve it for V initial. So V initial squared equals to Q. 2 times Q times delta V and divided by M. And again, whiteboard magic. Let me erase this 2 and put a square root sign. Let me compare with, yeah. Yeah, it's initial. We want to find the initial velocity that we have to provide. It's a whiteboard black magic. Oops. I didn't plug numbers. I don't like plugging numbers. I like dragging symbols. Okay, so that's the energy approach. Again, the only trick over here, be careful which point is initial, which point is final, because if I give a problem like this, I'm sure that about 40% of students would try to hide that minus somehow, or it's a very common word. So, okay, so now let's solve exactly the same using the force approach, and then the next problem will be somewhat easier. So now, approach number 1. So, for the force approach, now we have to deal with vectors. And immediately, you remember what we need to show, just to be safe. Coordinate system. I would introduce coordinate system. Even here, I would have, you remember, I started looking what point final, which point is initial, where x is 0, where x is not 0. But anyway, so let me introduce coordinate system. And you remember where the reference point is at the negative electrode. Yeah, exactly. So that's our x. This is 0, and this is d. Okay, so now we need to write down expression for the force, then apply Newton's second law, then kinematic equations, typical steps. All right, so maybe I will immediately show it sort of skeleton of the solution like I did in the lectures and in my recitation classes. At the end, we need to find what? Velocity, right? So in order to find velocity, we usually use what? Basically, I'm trying to discuss steps starting from the very end. at the very end, we need to find velocity. It's one of the kinematic parameters. Position, velocity, acceleration, 3 levels of kinematic parameters. And of course, they're all connected with kinematic equations. And of course, essential ingredient of those kinematic equations is acceleration. So in order to find any of those kinematic parameters, we need to find acceleration. Then, in order to find acceleration, we need to know the expression for the electric force. Okay, force in general, in this case, electric force. Then, in order to find this electric force, we have to have information about the electric field. And can we find the electric field from what is given? Potential difference is given, but we can easily connect the electric field with the potential difference. Okay, we will see the formula, right? But I'm sure that most of you remember it. So delta V. So that's the skeleton of the solution. So now let's do it. First step, from the potential difference to the electric field. Delta V. How is delta V connected to electric field? Essentially, it's this, Ex, right? The electric potential at the negative electrode is 0. Electric potential at the positive electrode is E times D. So the potential difference is E times D. Right? So from here, as a result, we will get electric field equals to delta V divided by D. It's a magnitude. But what's the direction of the electric field? Of course, we know from plus to minus, right? From positive electrode to the negative electrode. So the electric field is this way, from plus to minus. So this is E. Okay, and as a vector, electric field, positive or negative? On the picture. Electric field points to your right, and it's a negative x direction. So if you want to write it as a vector, of course, you need to write it as a negative vector, one-dimensional vector. Okay, so I want to write it as a vector. So E as a vector equals to delta V over D, and in the minus I hat direction. I just want to get acceleration, positive or negative, carefully, right? So without sort of guessing. Okay, so that's the expression for the electric field. And now force, electric force, Q times E. We're dealing with electron, which is a negatively charged particle, so it's a minus Q. And our electric field is also negative, so it's a delta V over D minus I hat direction. Two minuses. As a result, force is positive. Positive force, yeah, it will be that way, decelerating our electron. So the force will be positive, which is correct according to our picture. So it will be absolute value of the charge, delta V, divided by D, and in a positive I hat direction. So now acceleration, just divided by m essentially, right? To get acceleration, Newton's second law, using Newton's second law. So F now equals to mass times acceleration. So acceleration will be equal to F divided by m. So just add m to the denominator. So it will be Q times delta V divided by m times d. And acceleration is positive, which is great. So in our kinematic equations, we can just use positive acceleration. Because if acceleration negative, of course, in our kinematic equations, we need to use minus. Can we use kinematic equations after this? Which test do we have to run? Acceleration is constant, so yeah, great, we can use it. We can use kinematic equations. If accelerations are not constant, it's illegal, right, to use kinematic. It would be illegal. So equals to constant. So kinematic equations can be used. Okay, so now I need to move, probably separate it like this. So which kinematic equation would be the best? There are three of them, you remember? It's first one for the velocity, v naught plus at, then position, predict the future of the position, v naught t plus 1 over 2 at squared, and then no time equation. Huh? The last equation, I tend to agree. Of course, it's a, Okay. So, if we try to use the first equation, we need to find the final velocity. No, the final velocity is 0. We know. Initial velocity, that's our unknown. Acceleration we found, but time is also not known. So two unknowns. Of course, it's not the end of the life, right? So we can go to the second equation and find travel time. But we will have to make two steps. First, solve this quadratic equation for time, then go back and find velocity. But essentially, we try to combine this. But what's the major feature of the last equation? It's called no time equation or something like this, right? So essentially, it's derived or designed for the cases where time is not given or the question is not about time. So in our case, and that's our case, time is not given. We don't have any information about time. And the question is not about time. So most likely that equation number 3 will be the best in this case. Again, it's not the only one. Combine first two equations and solve it. And that's actually what we do in order to derive equation number 3. We just combine the first two equations. Okay, equation number 3 is the easiest. So it will be v final squared equals to v initial squared plus 2a. And delta x. Okay, so let me first write in general. So it's by definition, it's x final minus x initial. And now let's carefully look at the picture and assign the values. We want final to be 0. That's our goal. That's our unknown. Acceleration we found. Final position. It's this, and the final position is 0. Final position is 0. Initial position, it's over here, and it's d. Right, so be careful, because otherwise you will start getting some additional minuses, and of course, then you will be trying to hide it somewhere. And I usually see that immediately, right? So equals to d. Right. Okay, so now let me first rewrite it. So 0 equals to v initial squared minus 2a d. So now 2ad goes to the other side with plus. So that minus actually important. So v initial will be equal to square root of 2ad. Okay, so now we can plug acceleration. And of course, the answer is going to be exactly the same. So it will be 2. Acceleration is q delta v d divided by md. Yeah. All right, where's my, yeah. So d can be canceled, not d gets canceled. You see? And so we're getting exactly the same answer 2q times the potential difference divided by m. So what is, for me, strange about this problem, d is given in the problem, right? 1 centimeter. But actually, in our solution, we didn't use it. Sometimes they give us these numbers in order to, for example, to convince ourselves that this is a parallel plate capacitor. But here, we don't have any information about the area of the plates. So essentially, even from that point of view, that information about d is kind of useless, right? If they give us an area, so no, 5 square meters, 5 square meters, right? And then, of course, 5 centimeters, so it's a decent parallel plate capacitor. But essentially, this d over here is kind of hanging. Okay, strictly speaking, it's a kind of poorly designed problem. Right. Not poorly, just one piece of information which is not actually needed. Okay, this is that approach. There's another energy approach problem with 2 charges. You can look by yourself if you want. So let's solve now this problem, which is easier. And after that, transition between these 2 quantities, and let's call it, and we will call it today. Yeah, we will be able to finish it within half an hour. Good? Awesome. All right, so now I can start erasing this. Why I am recording this exam review session by myself? Because, yeah, school can record over there. There's a camera. But it has a fish eye lens. Once I asked to record it, and basically, you know what's the images of a fish eye lens, right? So essentially, everything is so distorted that it's impossible to understand what is on the whiteboard, right? Of course, it can record from the computer, but I don't use computers. So as a result, I had to come with my own camera and record it. But I like this room. It's nice. Not big, not small. So problem number 8. So again, motion of the charges. But now let's assume that we have 2 point charges. Here we had a point charge inside of a uniform electric field. Now 2 point charges. So you know what? Let me describe the situation, and then I will write what needs to be found. So let's assume that over here there is a charge, I don't know, positive Q. Actually, we will have to find it. But for now, in order to describe the situation, so. And let's assume that this charge is stationary. I know, it's nailed, grounded, whatever. We hold it. Maybe at some point it wants to move, but we hold it. So it's stationary. Then we will take a proton at infinity. So this is proton. R equals to infinity. And let's shoot it towards that negative charge, or towards that Q capital, with initial velocity V0 equals to 1 times 10 to the power of 7 meters per second. 1,000 kilometers per second. Not a bad speed. So it's a charge Q, small, let's say. And so, yeah, we assume that this is positive charge. And of course, this proton, it is going to do what? It is going to fly towards that Q capital, decelerating, right? Decelerating. So this proton is going to fly, decelerating. And of course, at a certain moment of time, it will stop for a moment, turns around, and start flying in the opposite direction. So for whatever reasons, let's say we don't want for this proton to cross a certain distance. Let's say we don't want that proton to get closer than the distance r from this positive charge Q capital. So essentially, we want to calculate how much of charge should be over here so that the proton would stop and turns around at the distance, at a given distance r. I know, forbidden region. The proton shouldn't get into that region. It's called like private space, right? Or something like this. No protons allowed. Right. So this is V final equals 0. So now let me write the question. So we need to find Q capital, which would stop a proton at r, at the distance r. Okay, essentially problem, I know, physical or philosophically very similar to the previous one. Again, we can use two approaches. Energy approach, force approach. Right? Which approach should be used here? Or maybe must be used? Okay, let's imagine if we try to use the force approach. What's good or wrong with that? Too many variables. It's a good reason. Okay, let me start. Let me start with the force approach. Wait, it's the first one. All right, force. All right. So, force approach, of course, is based on force. 2-point charges. So, which law do we have to use? Coulomb's law, right? Coulomb's law, 2-point charges. Yeah, exactly. Force approach, F equals K, Q small, Q capital over the square of the distance between them. So then, of course, next step, we usually find what? Acceleration, right? Moving towards the kinematic equations, right? So then, of course, so acceleration will be equal to F divided by M. Right now, I don't care about the direction. You understand in a second why. Later on, of course, I will start looking at that. So, of course, as a result, acceleration will be equal Q over mr squared. And after that, we usually use kinematic equations, right? So, which kinematic equations should we use? Oh, one from the last problem, right? Are you sure? Any other ideas? They're so negative. No, we cannot use them. Right? Okay, why not? Yeah, you remember every time I'm bugging you about what do we have to check before we can start using kinematic equations. Acceleration must be constant. In our case, is acceleration constant? It's a function of r. What happens with r? That proton is approaching that Q capital. R is getting smaller and smaller and smaller. Acceleration is a function of time, position, whatever. So it means that we cannot use kinematic equations, right? So it will be just illegal. Right? Of course, it's not the end of the life or whatever, right? You can still, in that case, you will have to solve second-order differential equation. Big deal, you go and solve it. But of course, it's much more complicated, right? So let me emphasize. So it's a function of r. So it's a f function of r. All right. So acceleration is not constant, and as a result, kinematic equations cannot be used. So it means that this approach, oh, no, it shouldn't be. As I said, it's possible still, but more complicated. Right, so, no, what I just wrote. All right, so I will write more complicated. No, of course, still, what is acceleration? It's r double dot. It's a second order, second derivative with respect to time. Okay, solve differential equation, right? So still possible. But again, relative to the energy approach. Right, so let's go back as a result to the energy approach. So and exactly the same total mechanical energy at the initial moment of time, or initial point, equals to the final. So initial point, of course, it's at this, at infinity. Right? So essentially, this is r initial equals to infinity. Final point, it's the point where we want to stop this proton. So this will be the final point. And now again, keep diving. So k initial plus u initial equals to k final plus u final. And at this point, students start making mistakes. Not in kinetic energies. Kinetic energies are obviously, which actually kinetic energy is 0. Final, again, we want to stop at a certain moment, like over in the previous problem. So final kinetic energy, of course, 0. All right. So because v final equals 0. But the problems over here, not the, I don't know how even to call it. Students just use the wrong formula for the potential energy. I don't know why, but I know 30 or 25% of students, they just grab this and start using that. And every time I have troubles, it's a big mistake. Right? So the system is 2-point charges. So we have to use this. So u equals k q small, q capital over the first power of r. Okay, so now let's just write down. What do we need to find? R. Initial 1 over 2 mv naught squared. Potential energy, initial. Yeah, what's the value of the initial potential energy? Yeah, 0, because r is infinity. So over here, let me write, so u initial equals to k q over r initial. So this is equal to infinity, of course. As a result, potential energy is 0. So this can be also dumped. It's essentially our reference point. That's our reference point in infinity. Right? And so on the right-hand side, only one term left. So it is equal to k q small, q capital. And the final point is at the distance r capital. So instead of that r small, there must be r capital. Right? So mass, of course, we know mass of the proton, velocity given, k constant, q we know, q small, r given. Essentially, we want to stop it at a certain point. We want to find q. So one equation, one unknown. Again, let me write. So this r actually. Okay, I didn't use numbers, right? So r is, let me write. So it's given. So let's solve it for q. R will. Wait, I said we need to find q and start writing r. All right, so r goes to that side, so it will be mr v naught squared over 2k q small. Okay. again, it's also at some point a few years ago, I gave this problem on the exam, the first midterm exam. Most of the students do well, except for they use the wrong formula for the potential energy. It's so depressing to see that seriously, right, guys? All right, so there's another example. You can look by yourself. OK, so the last two pieces about these transitions, and enough. OK, any questions about this problem? Yeah. I don't expect any questions about this. So probably let me start with that transition. So this will be 9. So what if we have this plot given information about the electric potential? V, units of volt. Then let's say x in meters. And 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And there 1, 2, 3, 4. Enough. And then minus 1, 2, 3, 4. OK, now the plot. So from 0 to 3, it goes up linearly like this. Then over 1 meter, it drops to negative value. And then it stays constant. So essentially, OK, I'll wait. Information about the electric potential is given. We want to get information about the electric field. Essentially, it's transition from V to E. So let's just quickly do it. So it's from V to the electric field. One-dimensional situation. We see how electric potential changes with x. X changes, and something happens with the electric potential. So, of course, we can find only x component of the electric field. Y component is either 0, or we just don't know anything about it. Let's assume it's 0. All right. So E sub x equals to minus. OK, strictly speaking, it's a partial derivative, but we have function of essentially v changes with x only, so partial derivative, straight derivative, it doesn't matter. So let me write straight dv over dx. And at this point every time, since we have a straight lines, so how can we rewrite this formula? Instead of differentials, we can use a delta. Changes in v and changes over x over finite range of x. So let me write it. Since we have straight lines, so we can rewrite it as minus delta v over delta x. Essentially, it's a slope. If it's a straight line, it doesn't matter if you measure the slope over infinitesimally small x dx increment or over finite delta x, slope will be exactly the same. It's a straight line. So that's what I essentially wrote. So now, as a result, let's divide this problem into three: region number 1, region number 2, and region number 3, right, where we have straight lines, because the slopes will have certain values for each of these regions. So region number 1. All right, so it will be E1 equals to minus, okay, let me first write, so it's a V final minus V initial divided by X final minus X initial. So again, be careful with final and initial points. Usually students, at this point, students don't have any significant troubles. Final point 4, initial point 0, final position 3, initial 0. So it will be minus, so it's 4 minus 0 divided by 3 minus 0. So it's a volts per meter. So it's a negative 4/3 minus 4 over 3 volts per meter. Am I right? Let me just, yeah. So it's essentially, it's a negative slope. So you calculated slope, it's a 4/3 and minus in front. Again, the major problem, sometimes students forget about the minus. That's the only thing. So region number 2, exactly the same thing. E2 minus, what's the value of the final point? Negative 4. Then minus initial point 4. So it's a minus 4 minus 4, right? So there'll be two minuses. So final point minus 4, then minus initial point 4, and divided by the increment in x, 4 minus 3 volts per meter. So it will be a positive number. So slope is negative and minus in front, so of course the electric field is positive. So essentially here, electric field negative, again, it's a one-dimensional vector. It just means it points in the negative x direction. So in the region number 1, electric field points this way. In the region number 2, of course, electric field is going to point that way. Positive vector, negative vector, that's what it means. So, and of course it's a 1, so it will be just 4. I mean 8, sorry. 8 volts per meters. This can be among multiple choice questions, something like this, quickly to check. And region number 3. Okay, I didn't show it in classes or in the lectures, right? So you can do it by yourself, but it can be easily shown by playing with units. Newtons per coulombs or volts per meters, it's the same thing. At some point when I had time in the recitation classes, some extra, I used to show it, but then I usually guys, okay, if you want, you can check it by yourself. It's the same, volts per meters, newtons per coulombs. So the value of the electric field in this region number 3, yeah, 0. Slope is, I mean, the curve is constant, horizontal, so the slope is 0, so the electric field will be 0. Right, so 0. Right. Okay, so that's it. And, okay, the last one. Done? Can I? Great. Great. Of course, you can plot it if you want. So, okay, this is definitely the last problem. Number 10. Whew. So what if we have this graph Ex, units volts per meters or newtons per coulombs, the same, right? Volts per meters. All right, versus x in meters. And let me probably first write the values, so it will be 1, 2, 3. 1, 2, 3. And probably first I will draw the curve, and then I will write vertical coordinates. So it will be straight line. And so this will be 0.3. And at that point, the value is electric field 200. Then this point is minus 100 volts per meter. So let's just find potential difference between points 0 and 3. Actually, which way I wrote it? That between x equals 3 and x equals 0. So now, obviously, we have information about the electric field. We need to get information about the electric potential. So now the second bridge, or the first bridge. So now it's from the electric field to the electric potential, right? And that's the integral. So delta V equals to V final minus, okay, we used A and B. VB minus VA equals to minus integral from A to B. E, it's a one-dimensional case. So it's a EX dx. EX dx for one-dimensional case, right? Right. Yeah, area. Or, of course, you can integrate if you really want to practice integration. Of course, you can. No, you don't. OK, we'll do both. Yeah, exactly. So A will be 0, B will be 3. So delta V. Of course, yeah, the first option, it's an area. OK, let me write. It's a first option, or first method. So it's a minus area under the curve. Area between the curve, the line, and the x-axis, because sometimes I saw some strange areas students try to calculate. I actually never thought that it's, but live and learn. So, of course, it's this area, right? Because I remember a few students in the past, they just drew this line, and they try to calculate this area, which is, I've never even thought about that area. So it's between the line and the x-axis, right? So graphical interpretation of an integral. Right? So area of, OK, let me, to be precise, label it O, A, B, C, D, right? Area of that triangle, that complicated figure, triangle of O, A, B, plus area of the triangle B, C, D. So minus area of the first triangle, 1 over 2, base times height, right? So in this case, base is, it's a 1 point and then point B. OK, let me decouple them, because I even confused myself. I was looking at that. What is that? Point 1, x equals 1, and point B. So, of course, height is negative. Don't forget about that. So the area will be negative. So it's a minus 100. So minus 100 volts per meters. Base is 1 meter, right? So that's the first area plus second area. Again, 1 over 2. Height is 200 volts per meters. Base is 3 minus 1. So let's do calculations. So minus 50 plus 200, so it's 150 in the brackets, positive and minus in front, so it's a negative 150. So negative 150 volts. Or we can integrate. Come on, you should be excited. Integration. Wow. What OK, so let's integrate. Your departments warned us to push you. OK, at least we expose. I don't give much over, as you notice, in terms of calculus, don't push much. Let's integrate. So in order to do that, of course, we need to write down expression for electric field as a function of x. So it's essentially, in general, you remember, y equals kx plus b, where b is an intercept, k is a slope, right? So in this case, it will be 100x minus 100. You can easily check it, right? So, but again, let's check it. When x equals 0, the value of e, negative 100. When e equals 0, what should the value of x? E equals 0, x must be 1. E equals 0, x 1 will be 0, equals 0. So this is the correct function, right? You can easily construct that. OK, so now, OK, let me factor out 100. So it will be x minus 1. And so now let's integrate it. So delta v equals to minus integral of ex dx from 0 to 3. Of course, most likely I will not ask you to do any integration in the, on the exam, but it's Friday evening. Let's integrate at the very end to ruin your weekend. Sorry. So 100 x minus 1 dx. Come on, what can be easier than integral like this? 100 can be, of course, taken outside. So it's a minus 100. And then integral of x minus 1 dx. So first integral, x dx. X squared over 2. Right? Yeah. Yeah, minus in front, so 100. So it will be x squared over 2 with the limits from 0 to 3. And then x, 1 times dx. Integral of dx is just x. Right? So it will be minus x from 0 to 3. So plug it, plug in numbers. Minus 100 there. So 3 to the power of 2 divided by 2 minus 0. So it's from the first limits. Then minus 3 minus 0. OK? So it will be negative 100. He decided not to ruin his weekend. I decided to be mean at the very end. 4.5 minus 3. The same negative 150, right? You see. I need to delete that from the video. So the same. But of course, calculations of area, of course, easier. But of course, it's only in this simple case when you have a linear function. OK, guys. 3 hours, almost exactly, right? So we started a few minutes later and we finished a few minutes later.